Hey, this is Leach with Sims and Math, and in this video, I'm going to be doing some examples of geometric and binomial distributions, how to answer them using technology. I'm going to be modeling it sometimes on Desmos, sometimes on the 84, and sometimes on Excel. I might not do every problem on every type of technology, but I'll be talking about the three pros and cons as we kind of go through them. So let's get started with this first question. Suppose a computer chip manufacturer rejects 7% of the chips produced because they failed pre-cell testing. Assume the bad chips are independent. Complete parts A through D below. So we're tasked to find the probability that the seventh chip they test is the first bad one they find, then find the probability they find a bad one within the first 8 they examine, find the probability that the first bad chip they find will be the fifth one they test, or the first bad chip they find will be one of the first 3 they test. All right, so first, notice all of these are geometric. If you're a little unfamiliar with geometric, this is the waiting time probability. This is the probability until you get a first success. Once you get your first success, you stop. Admittedly, especially B is a bit poorly worded, because when I hear this, I don't see the first one. It would be better if this problem had they find the first bad one, not a bad one. I might write to the author to ask them to maybe adjust that, because it sounds like one bad one within 8. That one actually would be binomial, instead of their first one and then they're stopping. So because it doesn't really make sense for the computer chip manufacturer to just stop testing, to stop checking them. Like, oh, I found a bad one, and they stop. But I do know that these answers are all following the geometric one, even though it might be poorly worded. So all these are geometric. You go into, you get your first success. At the end of the day, with some of these, the probability of calculating it is not too terribly hard. So let's make sure that we're good with this, with how this is done. So for letter A, find the probability that the seventh chip they test is the first bad one. Well, it says that there's a 7% chance that it is rejected. So that means let's have P be the probability of rejection, which is this 0.07, and Q will be the kind of the failure. So in this case, finding the bad one is the success, and finding a good one is a failure. Let's have Q be the probability of finding one that works. Oh, whoa. My screen scrolled up on me. Let me add this a little bit clearer. Let's have P be the prob of a bad chip, which is 0.07, and then Q is the probability of a good chip, which is going to be 1 minus that, or 0.93. Notice the probability of getting a chip that is good is kind of our failure here, but that's a 93% chance. So if I find the probability that the seventh chip they test is the first one, bad one. So in general, I'm going to get a bad, or actually, I'm going to get a good one. I'll do G for good. Good, 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 good. That's 5. 6 is good, and the 7th is bad. So notice it would be getting 0.93 times 0.93 times 0.93, and I'm multiplying because it's an and. I get a good, and then a good, and then a good, times 0.93 times 0.93 times 0.93, and then now times the bad one, 0.07. I don't want to write all those 0.93s, right? We can just use exponents to speed this up, and we can get 0.93 to the 6th times our 0.07. Do note that this 6 is notably 7 minus 1. So in generic form, this geometric distribution, its probability of x equals whatever the probability of your x is going to equal to our q raised to the x minus 1 times p. Notice it's this x minus 1 because if this is the 7th one, I want this exponent to be 6, just like we saw there. So we're going to be using this in some cases to kind of force the geometric to happen, because honestly, this geometric one, the 84 is the only one that kind of wins out here. So if I do this multiplication, let me switch over to my calculator. Just do this on this 84. And I'm going to do 0.93. I can make this, you can see the big screen for this. So if I do 0.93 to the sixth, get out of the exponent times 0.07, we're going to end up with 0.045, which is what we have over here. All right. So this is called the geometric probability. Notice the math we just did, we can easily do in any calculator, whether it's the 84, Desmos, or the or Excel. The 84 does have a benefit because it has a built-in geometric distribution. I can't find it on Desmos and nor Excel. So let me show you where it is on the 84. So press second, distributions, which is the vars key. So second, vars. Vars is left of the clear. I think you can see my mouse. Maybe wiggle a lot. All right. Then I see a whole bunch of continuous distributions. We're not using those, not yet. So I'm going to arrow up, and here are some discrete distributions. Most of my courses, I usually tend to skip the Poisson distribution. It's a great distribution that can model the number of Prussian soldiers kicked to death by a horse, which is true and funny, but maybe not because it's death. Notice you see binomial here and then geometric here. The geometric PDF is what I'm going to show you. It's not that big of a deal because it's just that math. I would rather just type in that math than get to the geometric PDF, but we will be using the CDF in just a second. So if I do the geometric PDF, it's going to ask me what's my P. This is my success, which in this case, the success is getting a not working computer chip, which if you're, trying to filter out the ones that don't work, that's kind of a success. You're like, oh, good, I found one that doesn't work. I'm glad that didn't get sent to market and a customer be upset. So I'm going to put in my P. This does need to be as a proportion between 0 and 1. And then put in the value of X. This is my number of successes until a failure. So this is my, number of failures until a success. So this 7 is my first success. So I have 6 fails, 1 success. Some other books or cases might define the geometric differently. The 84 defines that success as that 7th time. All right, press paste. And it's going to do the same math that we did just behind the scenes. It'll do it for us and we get the same value. All right, let's take a look at letter B. It says find the probability that they find a bad one within the first 8 they examine. Again, this wording is a bit different, a bit poor. I'm going to say that they find their first bad one within the first 8 they examine. That might be redundant with the first, but I think they kind of need it like you see on D because it doesn't look a little bit right. It sounds bad, but the answer at least is geometric. So let's just assume the best here. So that means that they're going to be looking at the first 8. So what's the probability that it is in the first one? Let me scooch this up just a bit. That could be the first one, plus the probability it could be in the second one, plus the probability it could be in the third one, plus the probability it's in the fourth, or the fifth, or the sixth, or the seventh, or the eighth. So we're going to be adding up all of these probabilities. So just to be clear, this first one, if I have no failures, I only have 1 success, this would just be the 0.07. Just that 7% chance of just randomly pulling a chip and it's bad on the first attempt. What about if it's on the second attempt? Well, that would be getting a good one, my failure, times getting the bad one. Notice this does follow. Both of these do follow. Let's take a look at our exponents. This is an x minus 1 situation. So technically there is a 0.93 to the x minus 1. My x is 1. I have 1 minus 1, which is 0. Any non-zero raised to the 0 power is 1. So this right here is just 1 times this. What about this? This is 2 minus 1, which is again just 1. or not again, but it is just a 1. So that's how our exponent is fine here. Plus, what about the third one? Now we can kind of clearly see the pattern a little bit nicely. I'm going to have 2 failures, so I'm going to mark that as a square times my success, times 0.07. We do that over and over and over, ever increasing that exponent until we get to be 0.93 to the 7th times 0.07. All right, so I could do this by hand. Worst case scenario, do all 8 of those by hand and add them up. Sorry, might suck. But we do have a way of speeding this up in technology. The easiest way is going to be in the 84, so let me show that one to you first. So let me turn her back on. She got a little sweepy. So I'm going to do, go back to where we did. I'm going to do second vars, and then I'm going to arrow up. You could arrow down, but the geometric is at the very bottom of the list. And let's grab the geometric CDF. So select that. Same questions. Our probability is 0.07. This X value, this particular one, this is the number, in this case, it's going to be our 8. It's going to be the furthest along our list, and it's going to add up everything from that number and less than. So if I put in 8, it's going to do exactly what we did. It's going to find when X is 1, 2, 3, 4, 5, 6, 7, 8, and add them all up. Notice, oh, I didn't mention the difference in PDF and CDF. PDF is it's called a probability density function. It's just used for a single probability. The CDF is the cumulative distribution function. It's when we have a cumulative number of things. By default, it's always equal to or less than. So that's what's happening here, kind of like a percentile, equal to or less than. If you're ever not sure about whether it's equal to or less than, just test 1, test our smallest one, and see if it's 0 or see if it's the number you think. All right, so then we hit paste, and it's going to do its work for us. I don't see the work behind the screen, but you do see that it should equal the number over there. Yep, 0.0440. All right, so that's nice that the 84 does that. How would I do this in, let's do, let me switch it to Excel first. Okay, so with Excel, I'm going to type in, let's do my trials, and then let's do well, I guess instead of trials, I'm just call this X. And this is P of X. Bold that for fun. All right, and then here are my X's. It could be 1, 2, and then I have established my pattern. I'm gonna swoop it down to 8. Right? And then I'm gonna find my individual probabilities here, and then I'm gonna add them all up. I'm gonna go ahead and get my sum of these things. All right, right now it's 0. So I'm gonna start with 3, because this is the one that looked like our probability. So I'm modeling these probabilities that we have right there to the left. I can point to them like so. I'm doing these. So I'm going to start with this 3 just to kind of model it, to make sure that that makes sense. So what I'm going to do, I can even kind of make a little formula here and say that I'll put it like here. That's kind of a weird spot for it. I'll put it here. I'll say that P is 0.07, and this will be my slot. Let's color it pink. P equals. And left align it because it's cute like that if I put it to the left, so it's by its thing. So P equals our 0.07, so I'm going to reference this. I could just use the 0.07, but you know, if I need to change the number around, then that'll be that. So I'll use that an absolute reference. So I'm going to say equal to. So I want my, I'm going to find my Q. Oh, I could actually be cute. Let's be a little bit extra cute. Let's do Q equals. Make it be right, aligned. And I'm going to do equals to 1 minus this. Just so that way that one's already done. I don't have to do the 1 minus. I'm going to color it B. I like to do the colors that I don't need to change, like a light color, just so that way they're there. Okay, so what I'm going to do, Then I'm going to do equal to. So my Q is going to be my 0.93. So I'm going to just say, I'm going to click that. So it's D3. Press my F4 for the absolute reference, because when I fill down, I don't want that to change. And then I'm going to say to the, and in my exponent, I want to do 3 minus 1. Now, when I did 3 minus 1, I clicked this cell because I'm going to want that to change when I fill up and down. So if I just do that, which this is not right, once you see what's happening, this would be this 7 minus 1. This is 4 minus 1. And notice this Q is staying in place. But I'm then going to after I'm done with that, I'm going to then multiply by my probability. And again, I don't want that to move, so I'm going to absolute reference. If you don't want to do this as to make it like a calculator, you of course could just type in 0.07 right here and 0.93 into here, and that would work the same. But it's just nice to kind of maybe build a little calculator if you want it. So now when I fill down and then also fill up, you could have obviously started with 1. It's just kind of nice for something that's a little bit more tangible and beefy with that 3. It lines up with what we have right here. All right. So notice we do get what we expect here for 1. We should get 0.07. And then this one does seem to be this 93% of 0.07. Okay. And then we get these numbers ever increasing, getting smaller and smaller and smaller. If I add all those sums up, notice what did we get? Did we get 0.0? Oh, yeah. Did we get 0.044? I misspoke. 0.440. Yes. So that's how we do it in Excel. In Desmos, it's a bit weird. It's basically the same thing. What I would do is I would add a table. Let's again do a similar list. Oh, let me make this be bigger. And I'm going to do 1. Try to be a little bit bigger. 1, 2, and once you establish your pattern, Desmos will follow you. Oops, I don't need to 9, just to 8. And then I can change what is in this, which is in this column. I think I can do equal to. Will it let me? Let me try to do equal to. And so what I'm going to, let me test this real fast. I actually didn't test the equal to before I started recording. If I did 2 times x1, is that going to be, oh, it's going to be angry. I need to get rid of this part. Okay, so what I'm going to do this math within this 2 times x1 right here, or this right here, but I'm going to be using x1. So we're going to use our math that we just did. And so it's going to be our probability of 0.93. I'm just going to go ahead and type in my probability of 0.93. That's my probability of failure. To the, I need to get an exponent. So I'm going to go ahead and put my my -1 first, because it gets angry otherwise. It's hard to get your, it wants to try to be helpful and move your subtraction down low, but I'm going to put my minus first to get my subtraction. And then I'm going to type in an x1. So ultimately I have an x1 minus 1 in the numerator, or sorry, in the exponent. Look what happened if I didn't do that exponent first, that minus first. If I typed x1 and then did minus, it tries to be helpful to move the minus down, and it's a little bit persnickety to get it back up there. So I'm just going to do the -1 first, arrow to the left, and then put in my x1. And then lastly, multiply by 0.07. So I know that's a bit jank, but notice these numbers are the same numbers we just saw on Excel. So what I could do is I'm going to copy this, Control C, and then I'm going to find that it's called the total is how it's treated in Desmos, is just the general sum of a list. So I want the sum of this list. I couldn't really name it because I didn't know how to name it. It wasn't letting me. So just grab this, and it knows those numbers. This is saved, so it's adding up those numbers, and I'm getting those. So it's not pretty, but it does work. It kind of saves you some time from typing it all out, or worst case scenario, type it out and add it up. Okay, so again, that one's not very fun, because that's not very fun if you're not using the 84. But that's how we do it. Just basically add it up. It's not hard, it's just tedious. All right. The other two, I think I'm going to skip because it's pretty much the same process. So find the probability that the first bad chip will be the 5th one. So that is This same process just without these two failures. So it would be a 4 here instead of a 5. And then the first bad chip they find will be one of the first 3. So it'll be this same process, but less annoying because it'll just be 1, 2, 3, and you just add those up. So it's the same thing, just easier. So I'm going to move on. All right. An Olympic archer misses the bullseye 13% of the time. Assume each shot is independent of the others. If she shoots 7 arrows, what's the probability of each of the results described in parts A through F below? Some of these are geometric, so she might not shoot all 7, so you just have to pay attention to the context. So let's define the things that we know. So here, P is a bullseye. Oh, sorry, P is misses. P is, I'll just say miss, which is 0.13%, or 0.13, or rather 13%. This independent is important for standard deviation reasons. And then N is 7 if it's appropriate. So there's my given information. So find the probability that, let's say her first miss comes on the 7th arrow. Notice that's geometric. So I honestly am not going to pull out a geometric distribution just to do this. So her first miss comes on the 7th. So it's going to be, we're going to have 6 bullseye, and then on the 7th one, miss. So the probability of missing is 0.13. So let's do Q, which is a bullseye. I'll just write BE for bullseye. And that is, I'll write just bull. I'll write bullseye. Stop being lazy. Bullseye is 0.87. So the probability of bullseye is this 87%. She's going to get 6 of those, and then she'll get a miss. So do that math, multiply that together, and that's what you'll get. Let's double check that to make sure that I'm not wrong. It's possible. I'm going to get rid of this. Let's do 0.87 to the 6th error out of the exponent times 0.13, and we should get 0564, and we do. Success. All right. She misses the bullseye at least once. Now, I'm going to show you in a second using the binomial distribution how we could do this, but think back to the beginning of chapter 5 or whatever chapter is, sorry, in my business stats class is chapter 5, or my regular stats might be chapter 3, whatever. Think back to the beginning of when you learn probability, that at least once has a little trick. Remember, at least once you do 1 minus the probability of no successes. So if I do 1 minus the probability of no successes, that'll give me the probability of at least 1. So in this case, if she missed the bullseye at least once, no successes, and my success in this case is actually a miss. So she has no misses. So this would be 1 minus the probability of all bullseye in 7 attempts, because we're told that N is 7. So I'm going to do 1 minus probability of bullseye is 0.87, and there's 7 of those. And we should get this probability. So let's do that. I'm just going to use Desmos as a guide for that. Or my calculator 0.87, and you can use any calculator to the 7th, and we get 0.627, and that's what we get. I did it right. Yay me. All right. Her first miss comes on the 2nd or 3rd arrow. Ignoring, this one's kind of ignoring the 7 because it's just, this is a geometric one. Let me scooch this math up just a bit. This is a bit of a geometric one. So let's have x equals first miss. I'm going to do y, because I want to use x later. Y equals first miss. So it's a probability that y is 2. I can write that neater. Plus the probability that y is 3. So you could do those two geometrics, or basically let's just add these up. So she's going to have a bullseye and then a miss. So probability of bullseye is 87, and then a miss, 0.13. Plus, then she's going to get bullseye, so that's 0.87 squared, then times the miss. So just add those two things up. Notice here, if I had to do, I would not do I would not do the fancy geometric distribution, geometric CDF on the 84, because if you put in 3, it's going to give you 1, 2, and 3, and then you're going to have to find 1 and subtract it from that. By the time I do that, I could just add it at these two numbers. It was annoying before because it was 8 numbers. Ugh, this is just 2. Easy. All right, let's do that. Get my problem to fit on the screen. All right, so I'm going to do 0.87 times 0.13 plus 0.87 squared times 0.13. I get 0.21, rounds up to 5, which is what the problem is. All right, now the fun part. Now we're going to move on to binomial. So she misses the bullseye exactly 3 times. All right, so now let's make sure that we're clear that this is a Bernoulli trial and this fits the binomials. So let's talk about bins. If you need to rewatch my videos about binomial, my video about binomial, again, it was long, but it did a lot of technology on there. Go check it out. So remember, it's binary, yes or no. Yes, because she's either going to miss the bullseye or make the bullseye. It's independent, it is. We have a fixed number, yep, at 7. Is it the same probability? Yes, the probability that she misses is 0.13. Okay, and so we have a fixed number. That's the thing that makes it binomial, and the question is asking about that, unlike this one, which wasn't asking about that. So notice here, this is exactly 3 times. I could have this. Notice that this one right here is not binomial because it's only about her first miss. There's a very specific order to it. That's why this is geometric. I'll emulate at least once. First, I'll emulate. I'll show you how to do at least once after I do exactly 3. My preferred method for doing the binomial distribution is Desmos because I can see it. I'll show you how to do it on the 84. I have to think about it on Excel because I don't remember. We'll see if it has a built-in function. That was the face of, oh, I should have tested it before I started the video. Okay. So let me clear out these things because we don't need this right now. All right, so reminder from my video, there is a built-in binomial distribution. Let's use it. You can just type in binomial dist, open parenthesis. That's great. If you don't remember that, the other day I was doing it, and I think I just misspelled binomial. I do binomial, M-A-I-L, instead of nomial, and I misspelled it, and I got real confused. Or it actually just came to the list and said this, binomial dist. All right, notice it tries to help us. It says, I need trials, comma, success probability. So let's input the trials, comma, the success probability. Or my trials, I see noted to the left is 7. Oops, my cursor needs to be inside the parentheses. And notice, Desmos is trying to help us out. It's wanting to graph something. It's wanting to do something. It's not wanting to give you an error. So it's saying, hey, my success probability is, let's say it's 0.5. It's just making one up for you. It's always going to default to 0.5. Is my success probability 0.5? No, it's 0.13. So I'm going to do comma 0.13. You can do the leading 0 or not. All right, now that I have that, I'm going to press zoom fit so that way I can see my graph a little bit more clearly. Cool. I like to go ahead and check the cumulative so I can see the sticks a little bit nicely. And exactly 3, let me adjust my scale a little bit. Can I get the numbers if I zoom in enough? Almost. Hey, give me ones. Give me ones. Get rid of minor. And it won't do it. Okay. Oh, well, I was just trying to make sure you could see the x-axis, but this is 0, 1, 2, 3. So here is my my ordered pair, or it is producing an ordered pair, but x is 3. The output is 0.0441, which is my answer, 0.0441. Now, I personally usually don't like just to click on it. This is a nice shortcut, but what if for some reason I needed more than 3 decimal places? Maybe especially if it was something like this and it's rounding to 0. So I'm wanting to get a few more decimal places. Then I would just put in the same min and same max. So if I said 3 to 3, notice I'm getting a lot more decimal places. Over here, when I was like, oh, what about if it's 6 and it was basically almost 0? If I do 6 to 6, notice to 4 decimal places, it rounds to 0. But look at all these decimal places that actually are calculated. So that's how you can get more decimal places if you need it. So the answer here was 3 to 3. All right, let's backtrack and talk about that at least 1. So if it's at least 1, it's everything but 0, right? So if I just delete my max, it'll give me a max of 7. I'm going to change my min to 1. So not the 0, but 1, 2, 3, 4, 5, 6, 7 all added up. And notice that is that same probability that we had because 0 gives me 0.3773. 1 minus that 0.3773 is this, which is what we saw on letter B. So do you see how that's how at least 1? It does fit the binomial distribution, but notice finding the binomial distribution, I mean, it works. It was just easier to do 1 minus probability of no successes. All right, what's next? Oh, let me show you how to do that on the 84. So let's do I'll do the 3, 3. I'll do the 3, and then I'll do the at least 1. Maybe. So binomial distributions, again, live on the distribution list. So I did second vars distributions. I'm going to pick binomial PDF or CDF. Specifically, I'm going to do the PDF just to get a single probability. So I'm going to do, I have 7 trials. My probability of success is 0.07. And my X value, my singular X value that I want is 3. And I can hit paste. Pro tip, this 3 is actually optional. If you leave that blank, it'll return all X values. That's sometimes helpful to maybe put that into a list for you to be able to add things up kind of on your own if you want. I'll show you that in a second. So hit paste, and it will give you that 3 that we saw a second ago. Is that the right answer? That doesn't feel right. Oh, because it's not 0.07. That was our previous problem. It's 0.13. So I can just manually change it. So just typed over that 0.07 to be 0.13. And there we go. There's our 0.044 rounds to 1. All right. Notice how I said that you could just not have this X. If you just didn't have this, whoa, moved on me. If you just didn't have this X, let me just delete this X. It would give me all X's. This one X is 0. I'm going to press, I haven't pressed anything except for now the right arrow. This is when X is 0. This is X is 1. Arrow to the right. Here's when X is 2. Arrow to the right. Here's when X is 3. Notice that's what I just found right there. Arrow to the right. Here's when X is 4. So one thing we could do is we could go to stat, edit. You could type in 1 through 7 just kind of for grins. 1, 2, 3, 4, 5, 6, 7, just so I can see them. I'm going to come over here and I'm going to arrow up into the L2. And here's where I'm going to input in. So in this screen, I'm going to press second vars distir, binomial PDF, and I'm going to delete this 3. So, oops, and I'm going to put this back to be 0.13. So 7 trials, P is 0.13, and I have no X. And when I paste it in, oh, I need zeros, my bad. This needs to be 0, 1, 2, 3, 4, 5, 6, 7. That's where I wanted to do that. So now, notice what happens. Now I can see these are my X values. These are my X values right here that are all calculated. So when X is 0, I have no successes. I get this 0.3773. When X is 1, I get this. It's the same thing I got on Desmos a second ago. Obviously, Desmos is faster, but maybe if your instructor won't let you use Desmos, here's that. So if I wanted to find at least 1, I would just be like, oh, it's 0 and do 1 minus this to get the rest of those added up. If I wanted to do this using the CDF, it would be dumb. I wouldn't do that. Let's look at the next question. Let's do the next ones are at least 3 and at most 3. I'm going to do the CDF for that because I would not do CDF for this because it's kind of stupid. Okay, let's do the next 3 questions. I'll do them on Desmos and I'll show you on the 84, and then I'll think about Excel at the end. All right, so this says she misses the bullseye exactly 3 times. We did that. So now we're going to do at least 3 and at most 3. I've talked about this before, but I draw mentally a number line, and I kind of do it with my 3 fingers. So just to show you what I'm doing here, I draw 3 numbers for at least 3, at most 3. So I will reference the number, my middle finger here will be the number that I want, which is the 3. Then I think about the number below, which is, where's empty space we can see. Now move your head. Okay, I'm a teacher, I can do this. So this middle number is the 3, the number below is the 2, the number above is the 4, if I did that in the right order. But I tangibly touched as I imagine that this is a number line in front of me. So then why I test, is 3 at least 3? Is 3 at least 3? Yes. Let's do 4. Is 4 at least 3? At least 3, yes. Is 2 at least 3? No. Sometimes I have to say it out loud because it hurts my head. That time, honestly, I was confused whether it was 2 or 4. Then it was for the at most 3. I got this one. So it's the same, 2, 3, 4. Is 3 at most 3? If I kind of, the reason why what I think about here, let me backtrack for a second. If I was to ask my husband to give me, let's say he's going to go in the kitchen. I was like, oh, bring me some cookies. Especially those HEB ones, those Texas pecan. Those are so good. But if he said, oh, how many? I said, oh, at least 3. If he brings back 3, I'm happy. If he brings back 4, I'm even more happy. If he brings back 2, I'll be sad because I said at least 3. But what if I said at most 3? Well, is 3 at most 3? Yeah. Is 4 at most 3? No, that doesn't sound right. That's too big. It's 2 at most 3. Yeah. So technically, if I said, oh, bring me back cookies, he's like, how many? I said, at most 3. If he brings me back 0 cookies, that would satisfy what I said, but I still would be sad because I didn't have cookies, but it is what I asked for. So notice this is going to be 0, 1. This satisfies 0, 1, 2, 3, 4. At least 3 is 3, 4, 5, 6, 7. So it's 3 and bigger, and this is 3 and smaller for at most. All right. So let's take a look at these 2 problems. So on Desmos, it's real nice because we can just look at it. So if it's 3, at most 3, I want 3 to my max. And notice when I do that, I get my answer, 0.0513. And visually, we can see this here. Here are these, it's 3 or bigger. What about if it's at most 3? Well, now my maximum is 3, and my minimum is that 0. So this is these 3 numbers being added, these actually 4, 0, 1, 2, and 3 being added up. And that's where I get 0.9928, which is also what I have on the screen on Desmos, 0.9928. All right, let's do it on the 84. The 84, the at most 3 is actually going to be a little bit easier because the way that the 84 works, just like the geometric, it is a less than or equal to. So I could, in my stat here, since I have stat edit, I could just manually add these numbers up. Since I've gone through this work, I could do 3 or bigger. I could just add these up. Add these up to 4 decimal places and they'd be good. Oh, spinning wheel of death. Please hope my computer's not breaking. Okay, can't panic for a second. And then for at least 3, at most 3, I mean, I could just add these 4 numbers up. It's that easy. But there is a way to do the addition for you, especially if there's a lot of numbers. So I'm going to do second distr, again, second vars for distributions. And this I'm going to do binomial CDF. Remember, the C is cumulative. So I'm going to do the cumulative. I have 7 trials. P is 0.13. I'm going to do the at most first. So this is I want to find 0, 1, 2, 3 and add that up. Because if I put in the 3, that's what's going to happen. It's going to give me 0, 1, 2, 3. And then press paste. So when I add that up, I do get the number that I was expecting, 0.9928. All right. Now then, what about if I want 3 or more? Notice I didn't have a directional thing here. If you're working on an Inspire, the Inspire does beat the 84 here because the Inspire does have a min to max. For some reason, they didn't program in a min to max in the CDF for the 84. It's only a less than. So we kind of have to fake it. So, well, threw my Apple Pencil around. So on my map here, notice I want 0, 1, 2. I want, I misspoke. I want the 3. I have to zoom out and it'd be all weird. Okay, I guess you can see this here. So I want the 3, 4, 5, 6, 7. I don't want 0, 1, or 2. So what I'm going to do is I know that all of this should add to 1. So if I do 1 minus this part I don't want, I'll get the part I do want. So I'm going to go ahead and type into the calculator 1 minus, and then I'm going to run a binomial CDF, but this time it's going to be less than, it's going to be 2 or less. So I could run through the whole process, but a shortcut, I could just arrow up and hit enter. It's going to copy and paste it down. So do you see I have 1 minus binomial CDF? But I don't want it to be a 3, I want it to be a 2. Press enter, and I get my answer of that 5%, 0.0513. So that's how to do it on the 84. It only behaves less than. So if you want a greater than, you need to do a 1 minus. If you want to do a between, so just to model, I know this isn't the question, but if I wanted to do, let's say, 3 to 5. Now I could just find these 3 numbers and add them up. Or on Desmos, obviously we just do 3 to 5. On the 84, I'm going to have to do, so notice the answer is 0.0512. On the 84, I'm going to have to do the binomial CDF. I'm going to do my biggest one, which is the 5. So if I run this, this is 5 less than. Now I want 3, 4, 5. I don't want the 0, 1, 2. So if I do my answer minus, let me just run and just do the binomial 2. So this is the part I don't want. So then if I do this thing minus what I don't want, I'll then get the 0.05122, which is what we saw here on Desmos. All right, let me chance fate and look at Excel. I don't remember if we have a binomial. We do. I should have looked at this before. It wants binomial dist. It wants my number. It wants the trial, the probability, and cumulative. I think this hurt my brain at one point when I tried. Let me go to a new tab. Let's try it out live on recording. I'm not editing this, so let's find out. So I think, let me test this real fast. Binom, but the binom dist. I think if I said the number, what is this thing? Hover over it. Is that going to help me out? Number S. Trials, number S. What's number S? Oh, probably just my X. Okay, so let's say this is the 3rd time. I have 7 trials, probabilities 0.13, and leave cumulative off. So let's do false. This should be the exactly 3 then. Yeah. Okay, that works. So notice here, so this number S, the number of successes, That's probably what that is. That is my x. There's my trials. There's my probability of s. And then do the cumulative. So if I change this cumulative to true or 1, it's then going to give me the area there or less than. That's nifty. What's the binomial dist range? Returns the trial results using the binomial distribution. So if I have 7 trials, the probability of success is 0.13. And then I want the number 3 to 5. Yeah. So here's how to do the range, which is what we did just a second ago, which is also helpful for being able to do those multiples. So there are those 2 formulas. How about that? Figured it out fresh on air. Okay. Last one, real fast. And it's, oh, I should have worked one of those in it. No, I know all these. Wait, just went blank. Okay. So last one, and this is just some means. These 3 you need to use a formula. So this is the same situation, but our things have changed. Says an Olympic archer is able to hit the bullseye 84% of the time. She got better. Assume each shot is independent of the others. She shoots 7 arrows. How many bullseyes do we expect her to get? So this is a binomial. So the expected value of a binomial distribution, I'll just do mu. The expected value of the binomial distribution is n times p. So in this case, n is 7, p is 0.84, because in this case, our success is her getting a bullseye. So I'm going to do 7 n times p, 0.84, and we end up with, we should get the 5.88. This should be pretty intuitive, that it's just n times p. If I have a 6-sided die and I roll the die 6 times, how many 5s do you expect I to get? 1. If I roll that die 12 times, I should get 2 5s on average, right? If I roll it 24 times, I would expect 4 on average. Decimals could happen, right? If I roll it once, I would expect on average a sixth of a 5. I get a 5. How many 5s do you expect 1/6? Now that's weird, but remember this is the average. So n times p. The standard deviation is going to be, let me write that a little bit neater. The standard deviation is going to be the square root of npq. Standard deviation, the square root is a bit long. Square root of npq. So this is going to be the square root of 7 times 0.84 times q is 1 minus p, which is 0.16. Oh, she actually got worse. I promise I teach math. So we do that multiplication and we do end up with 0.97. Lastly, the question is, if she keeps shooting arrows until she hits the bullseye, how long do you expect it to take? This is going to be, this mu, this is geometric. And the mu for the mean for geometric is just 1 over p. So again, let me return to the die. So if I roll a die, a 6-sided die, how long until I roll a die until you think I get a success? If it's a 6-sided die, how long until I roll a 5? Well, on average, it should take me 6 times. That's intuitive because it's just 1/6, and you just do that reciprocal. So this is just 1 over p. So this is 1 over 0.84, which is just going to be 1.19 when you end up doing that math. All right. So I hope this helps seeing seeing these geometric and binomial ones, how to do these examples using technology, Excel, Desmos, the 84, how to kind of differentiate them. Sorry that geometric is kind of weird. If you have a lot of them to do, the 84 kind of wins. But at the end of the day, it's not hard, just tedious to have to add all those numbers up. All right, hope this helped. Feel free to like and subscribe, and I will see you in the next one. Bye. The like and subscribe is a joke, but feel free to do it. Bye.